Yes, you can
So,
start.
okay, thank you. So thanks a lot for the organizers for inviting me. I mean, it is really a great honor to be present in this conference and talk. So I have to say that I never met Rodney Baxter. So obviously I know the works, but somehow I'm on a different generation and we never met in person. When I was already working, then I didn't meet any conferences. Anyway, I from all of the works that I have, I selected a topic which is really about the basic things in integrability, namely Young-Baxter equation, and finding integrable models and finding new solutions to the Young-Baxter equation. So some of you might have heard one of these talks, but anyways, this is one of the topics that I really like from the last couple of years. So the topics is, as you can see, medium range spin chains or integrable spin chains. So what is this? So the idea is that normally when we are doing integrable spin chains, then most of the time people are doing nearest neighbor spin chains. So most of the times the Hamiltonian looks like this. That Hamiltonian is the summation over sides, and we have a two-side interacting model. And then this Hamiltonian density comes from some kind of derivative of Lax operator, in many cases it's derivative of R matrix. And then we have lots of works of obviously for finding such integrable models and analyzing such integrable models, etc. And then in recent years, there was some kind of motivation to study spin chains which have longer interaction range. So this is what we call medium range spin chains. When we have Hamiltonian, which is a summation over sides, some h localized at j. But now we have an operator density h of j, which is not two-side interacting, not two-side range, but maybe 3, maybe 4. It may be connect on 5 sides or some little bit longer, but definitely finite range. So I will not talk about Hardy-Shastri or these kind of things, which is definitely long range interacting. This will have a definite range, but bigger than 2. So what type of models appeared which made these studies interesting? I think the biggest motivation for us, for our work, was the so-called folder XXA model. So it's just a name. So folder XXA model, it comes from a special limit of XXZ model, a special large coupling limit of the XXZ model, but a non-trivial limit. Anyway, I will write down the Hamiltonian now. The Hamiltonian is the following. So h of j, Hamiltonian density, looks like this. We have a projector, 1 plus zj plus 3. I will explain in a moment. And then multiplied by xj plus 1, xj plus 2, plus yj plus 1, yj plus 2. So now I am using Pauli matrices. So x, y, and z are Pauli matrices acting on obviously the sides where the indices are. And then this is if you recognize the Hamiltonian density of the XX model. So if this would be not here, then this is basically not basically. This is the so very famous XX model solvable by Jordan-Wigner transformation, free fermions, etc., etc. This term describes you hopping. So when you have in a particle picture, when I have empty site and occupied site, then this term describes you hopping. So it describes the transition matrix elements from here to here. One particle can hop to a neighboring position with amplitude 2, actually. So this is this process. But then it turns out that we can have a Hamiltonian density like this, where these hopping processes are controlled by this projector. What is this projector? So this projector gives 1 if the spins on site j and j plus 3 have the same orientation in Z basis, and it gives 0 if they are of opposite orientation. So if we are talking about hopping processes like this, then there are the following hopping processes mediated or described or generated by this kind of Hamiltonian density. There are 2 types of hopping processes. So this was XX model. Now we have 4 sides. So one possibility is that this particle can hop here. So there are hopping processes to the left or right when these are empty. And another possibility is when this is also full. So this is also full. There is a particle there and one particle in the middle can hop. So there is a transition matrix element from here to here. And these are the 2 allowed transition matrix elements in this model described by this Hamiltonian density. And this Hamiltonian was derived actually by multiple authors. So actually, some very similar Hamiltonian appeared in the 90s, but in papers of some Indian authors. But then later, there were some people studying so-called Hilbert space fragmentation, and in a fermionic notation, they derived this Hamiltonian and modifications. Then there was also Maurizio Fagotti and collaborators who derived it, and then independently, we also derived it. So people actually didn't know about each other when they derived it. And everybody seemed to claim that this seems to be integrable, or maybe not everybody, but definitely Maurizio and our group. So it appeared integrable, but when we looked at this model and we saw Bethe ansatz, etc., there was no good theory to describe integrability of a four-site interacting model. And here I should really say a few words because I said a good way to deal with it. So one thing is in integrability that you can construct maybe coordinate Bethe ansatz wave function. And this was done. So Maurizio Fagotti and Leonard Zadnik, they constructed some kind of Bethe ansatz, exact wave functions, they checked it's good, works, etc. We also did something like this. Now the second thing that you might want to do is construct conserved charges. So you try to do somehow with hand or computer algebra, you convince yourself that there is a tower of conserved charges. So conserved means they commute with Hamiltonian, but also they commute with each other. And then maybe you believe that it works. And the third thing is that what is the algebra you can maybe most clever way is you want to go to Yang-Baxter equation. So you want to embed your charges into a transfer matrix, and commutativity of transfer matrix should follow from Yang-Baxter equation. There should be a Lax operator, R matrix, solution of Yang-Baxter equation. So then the question is, what can we do with a model like this? Because all of the things that we know in integrability, or not all, but most of the things that we know are Yang-Baxter equations applied to a model like this. And then there is an obvious thing that people can do, and actually, so when I give this talk, and many times people start with this comment or question. So if you fuse sites together, so let's say you fuse sites together, 2 or 3 sites together, and you make a kind of a transformation, a blocking transformation or something, then in the new picture, actually the 3-site or 4-site interacting Hamiltonian will only be 2-site interacting Hamiltonian. If you group enough pieces together, if you group enough spins together, then somehow interaction range obviously gets shorter and shorter, and eventually you will have an integrable model which is of this form, but with higher dimensional local space. So the answer is that you can always do this. So if you want, you can do it, and then you get something, maybe. But then we said that this is not satisfying, and for the following reason. We wanted to have a description or theory for these kind of spin chains when everything is translationally invariant in a really manifest way. So when you do this blocking transformation, like you group 2 things together and you fuse them or something, then clearly this breaks the translation invariant. It can be still a good theory, it can be still a solution of Yang-Baxter equation, what you get, etc. But translation invariance in a manifest way gets broken. So we wanted to have a new theory which is manifestly translation invariant, which like these models are translation invariant. And this is what we did with Tamás Gombor. So it's a paper from 2021. Actually, I forgot to write the archive number, but you can find it. So the title is Medium Range Spin Chains and Several Automata, or something like this was the title. Tamás Gombor and me. We wrote it. And actually, in that paper, the key idea of all of the derivations was to take all of the structures that we know from from the normal cases, to apply it to these cases in a way that we can do the blocking transformation, but we want to have this translation invariance by comparing various, at least 2 or 3 types of blocking transformations. I will explain this, and this will be now the main topic of my talk. And let's see how far we get. I definitely want to avoid too many technical details because there is clearly not enough time, and it's a whiteboard talk anyways. I will draw diagrams instead. So I just hope that that many people are familiar with these diagrammatic techniques of writing down transfer matrices, etc. I will try to explain it, but for really technical details and formulas, please go to the paper because this talk is not adequate to describe all technical details. So I will erase this and let me then start Actually, maybe I will write with the colored ones because this is difficult to erase. 1 second. So I will start now with the blue and green, and let me know if you don't see it. Then I will switch back to black. So first, let us go back to the normal case of nearest neighbor interacting. And how does the transfer matrix look like, and what is the Young-Buster relation? I want to show you a diagrammatic way of constructing these objects. And then I start with the so-called Lax operator. And for the Lax operator, I draw this figure. So maybe it's a little bit unusual. I put here a U, which is a spectral parameter. Maybe it's unusual notation, but for me, it is a convenient notation. So Lax operator is a tensor which has 4 legs, or you can view it as a linear operator which acts on two spaces. So it acts on auxiliary space. Auxiliary space is these horizontal lines. So let's say this is incoming auxiliary space index and outgoing auxiliary space index. And it also acts on the physical space. And for me, physical space will be vertical lines. So this is incoming physical index and outgoing physical index. And the Lax operator is then a linear operator, but you can view it as a 4-leg tensor if you want. And then from Lax operator, you can construct your transfer matrix. And then it looks like this, that you take product of Lax operators in the auxiliary space. And then it becomes an operator which acts in the physical spaces. So it acts on the tensor product of physical spaces. And then when we do this, then it is best to take periodic boundary conditions here. I will not draw it, but it is understood that here it's periodic. I connect these lines. And then you can prove that in many cases, this object, which I will call transfer matrix as a function of U, it actually forms a commuting set of transfer matrices. And to do this, you need the intertwining relation described by the so-called R matrix. And I will draw it diagrammatically. So what is it? I want to prove that T of U and T of V is equal to T of V and T of U. And then this is the train argument that many people write in all of these lecture notes and books, etc., etc. So I will not repeat the argument. I will just draw one picture, which is important. So I take product of transfer matrices, which means that I take 2 of these lines of Lax operators, and I on top of each other. They act after each other in time, so to say. And I want to intertwine them. So I want to have a situation where I have a product of Lax operators in auxiliary space, something like this. And here I have, let's say, V, here I have U. And then I want to make some kind of transformation so that these rapidity parameters get exchanged. So I want to have some kind of transformation such that eventually I will end up with this situation that here is V and here is U. And then to do the thing to do is we act with the R matrix on the auxiliary space. R matrix will have 2 it's also 4-leg tensor, but it will have 2 indices acting on the auxiliary space. And then we can write a thing like this. Maybe I will draw it with blue, that R matrix acts here. And then this is basically R of UV. And I can exchange it with the Lax operators. And then this will be the Young-Buster equation. So this is also R of UV. And by intertwining, so exchanging this 4-leg tensor, I can exchange the order of these Lax operators. And then I can apply the train argument. After inserting one copy of this, I can apply the train argument and prove this commutativity. So this is what we all know. And then the question is how to modify it for the medium range interacting thing chains. Because this will actually describe you local Hamiltonians. I need to tell you how to get local Hamiltonians. So there is this regularity condition that the transfer matrix at rapidity 0 is actually proportional or equal to, let's say, equal to the one-side shift operator. I denote it by U. And this typically comes from the condition that if you have the Lax operator and you insert 0 rapidity, then it becomes the permutation operator, which I put like this. So then this is a permutation operator which permutes auxiliary space into physical space and vice versa. And then if you use this condition and you substitute this at every place, then you get that this transfer matrix will actually become a one-side shift operator. And then you go further and you want to compute what is the derivative of transfer matrix at u equals 0. Actually, logarithmic derivative, you need to multiply with the translation with the inverse of u. And then you will get that it's the Hamiltonian. And actually, then you will get that the Hamiltonian acting on sides j and j plus 1 is basically the derivative of the so-called Lux-Check operator. I mean, now I will write the formula. So Lux-Check operator at sides j and j plus 1. Where this check, it basically means that I add the permutation operator. So it basically means that I rotate this picture like this if you want that. I don't know if this is clear or not, but basically this is the Lux-Check operator. I make just a rotation, which means basically a permutation. And I take this derivative at u equals 0. And then you end up with your normal integrable spin chain. Then what can you do? One more thing which is important is the so-called Reshet-taking condition, but I will talk about it later. I want to first move to the medium range spin chains before my timeline runs out. So for the medium range spin chains, we want to have a situation like this. So if in the medium range spin chains, the Hamiltonian density acts on 3 sides or 4 sides, it is very natural that somehow the Lux operator should also have more indices. So it should be a tensor which has more legs. And this is very obvious if we think about the blocking transformation. So I delete this. So let us assume that we have a spin chain and we have some kind of Hamiltonian density which acts on 3 sides. The next simplest case is 3 sides. If the Hamiltonian density acts on 3 sides, then I can do this blocking transformation like this. And then I will have these fused spins, if you want. And then if the Hamiltonian density acts on only 3 sides, then for the fused spins, I will have already nearest neighbor interactions. I mean, this is clear from the picture. So a 3-side interaction gives you already only just two-side interaction for the fused things. But then comes the problem that what I said at the beginning, that blocking the spins breaks translation invariance, and you can do the blocking transformation in 2 ways. Either you block these ones, or you do this type of blocking. So with one side shifted. And then our main idea was to derive this Young-Baxter integrability structure by enforcing that the 2 blocking transformations should give you completely the identical answer for the transfer matrix and all conserved charges and everything. So let's say we did the blocking transformation, we derived a certain kind of Young-Baxter structure, and then we asked what is the condition for the resulting objects such that it should be manifestly equal with the result from the other blocking transformation derivations. So if you do the blocking transformation, then you fuse 2 spins together. So if your local dimension was originally D, then after the blocking transformation, your local dimension will be D squared. And then instead of a blocking transformation, what we did is we said that the Lux operator and R matrix and everything should have just twice the number of legs. I mean, this is very obvious. So somehow, instead of this Lux operator that was originally, we said that for the blocking spins, blocked spins, we want to have an object which has twice as many legs. So a big tensor where I have 2 copies of auxiliary spaces and then 2 copies of physical spins. I mean, this naturally corresponds to a blocking transformation. It's very natural to assume that if we block 2 spins here together, then also the auxiliary space should have the same number of legs, so to say, or same number of same dimension, but it can be written as same number of legs here. And then we assume that this is the Lux operator. It also should have a spectral parameter U. And we use this Lux operator to build the transfer matrix here. And afterwards, we require that the 2 blocking steps should give you the same answer. And time is enough for this, so I will draw this picture, and then you will get the basic idea of what we do. So I draw the picture when I take these blocked spins and transfer matrices, and I take copies of this tensor. So in the first way, I have a tensor here, a tensor here, a tensor here, etc., and a tensor here. And then I have these auxiliary spaces, I connect them together. And then I have the physical spaces. So my transfer matrix would look like this. Now I do the opposite way also. The opposite way means a shift by one side. So I will have blocking transformation like this, etc., and so on. So here I also connect these sides, and then here would be the legs. I'm not taking now the product. So these are two separate objects. I'm not taking the product. I'm just drawing the pictures. And then this is the key step. What we did, we required that whatever is this object, this transfer matrix should be manifestly the same as this transfer matrix. And then this gives the idea. So how can we do it? We can do it if this block factorizes. So if this is a tensor which factorizes in the following way, that we have this, and this is actually equal to a product of two Laps operators like this, then the translational invariance is manifest. Because if I substitute this here, then everything factorizes and I get the product of these Laps operators, and also here, and it's the same. So this is basically the key idea, and we built the theory at this idea, so that we should have a Laps, in order to describe free-side interactions, we should have a Laps operators which has one physical index, acts on one copy of physical space, and two copies of auxiliary space. So if you want the Laps operator as a linear operator, will be like it acts on a physical index J, and it acts on one auxiliary space and another auxiliary space, if you want. We need to have an R matrix. An R matrix can again commute objects like this. R matrix will satisfy the Young-Baxter relation, and it will also commute things like this. So if I want to draw the R matrix, I will delete this one. If I want to commute the R matrix, then if I want to draw the R matrix, which describes me commutativity of transfer matrices, then again in the auxiliary space, in the physical space, I take two copies of Laps operators. This is U, this is V, and I make one more copy, and then this will be V, this will be U. And then in order to describe the commutativity, I again need an intertwiner, and the intertwiner will be the R matrix, which will have double number of legs. So if I want to draw it, maybe I want to draw it like this, just one possibility. And these are outgoing indices, and then this is R of U and V, and it will be an intertwining relation. So these two will be exchanged if I put it here. So I can put it here as an equation. So to say, I mean, I'm not good with drawing, but and then this will be my equality. It's also some kind of Young-Baxter or star triangle or whatever relation. It's an intertwining relation, and this is somehow like the basis of what we do. This is our RLL relation, and then we also have this is running out. I also have specifically another relation. So this is RLL relation. And we have also the R matrix satisfies the Young-Baxter equation with 3 copies of R. So how much time have I remaining? If an organizer could tell me.
What do you think, Vladimir? Is it?
I think 4 minutes.
4 minutes?
Okay, thank you. So, and then last thing what I want to say, and then this will be enough for the 4 minutes, is that using the Young-Baxter equation, we derived the generalization of the Reshetikhin condition. And this is very important because the Reshetikhin condition can be used to construct, find, perhaps even classify integrable models. And nowadays, there is a lot of activity in trying to prove the Reshetikhin conjecture, or actually maybe it's a conjecture of Grabowski and Mathieu. I will describe it to you very quickly. Not without much details, just the key idea. So the key idea is that you have a Hamiltonian, you have a boost operator. With the boost operator, you can, with taking commutators, you can construct higher conserved charges. And the Reshetikhin condition is basically that if you take a boost operator, you construct the next local conserved charge. If it commutes with the Hamiltonian, then from this, you can be assured that there will be actually a Young-Baxter equation solution or solution of Young-Baxter equation behind the theory. In more practical terms, it means that if you have Hamiltonian is a sum of H, J, and J plus 1, then you can, if you can find the following charge, which is a free side charge, which is of the following form, that it is commutator of H, J plus 1 and H, J plus 1, J plus 2. So if this charge with this density commutes with the Hamiltonian, then you have an integrable model. So this is the conjecture, that it is enough to find one conserved charge of this form, and then you have a solution of the Young-Baxter equation of difference form. It's a conjecture. And one part of this conjecture was actually proven very recently, 2 weeks ago, by Akihiro Hokio. I recommend that paper. Maybe it's really a good proof, but it's not accepted yet, but maybe. Anyway, what we did, and this will be my last message, we generalized this Reshetigin condition for medium-range spin chains, and it can be used to really find, construct, classify medium-range spin chains. So here the relation is that Hamiltonian should commute with this one. You try to solve it and solve it for H, and then you can find an integrable model. Instead, what we did, we have, for example, a three-side interacting model. So H, J, J plus 1, J plus 2. I will not write it down. So I want to save space. So this will be J, J plus 1, J plus 2. And then we said that for a Hamiltonian like this, we will have a five-side charge, some operator which acts on 5 sides. And it will have the following form, that H of J needs to be commuted with H of J plus 1 plus H of J plus 2. And our main result is that if you want to find integrable spin chains with three-side interactions, then you should look for cases when Hamiltonian of this form commutes with the 5-side charge of this form. And then this is much easier than finding solution to Young-Baxter equation, because this is just a cubic order 3 equation in the H. This is quadratic, so altogether the commutativity is cubic. And solving such a cubic equation is much easier than solving full Young-Baxter equation. And there is a hope that if this is satisfied that a Hamiltonian commutes with Q5, then you can later also find solution to Young-Baxter equation. And in all other cases that we looked at, it seems to be true. We didn't try to find the proof, so we just tried finding solutions, and we did. So we tried the solution for, we made this solution for Polderic 6A model, but also other models. There is not much time, I mean, no time remaining, so I will not give you more examples, but in other papers later on, we really found new integrable models with this technique on acting on 3 or more sides. So it's an effective method. And then also another thing that you can do, last sentence, you can look at the solution of Young-Baxter relation. I said that there is an R matrix, which it's big R matrix, but nevertheless an R matrix. And you can ask yourself, does this R matrix look like anything that you see in other papers or other models with quantum group symmetries, whatnot? And then it's a difficult task. And in one of the cases that we did, we looked at the R matrix, and we didn't know whether it's in the literature. We didn't say it is new, we just published it. And then one of my, well, not collaborator, but we discussed a lot with Andriy Liashik, and then he found that in one paper, this R matrix was there. So it's possible that we don't find anything new, but we have other cases where we have an R matrix and still we show it to people and they say that it's new, or they don't know whether it's there. So maybe you can find some cases which are really new, but it's difficult to know. So this was my talk. Thank you very much for the attention.
I have a question. You hear me?
Yeah. Yes.
Suppose you have x.
I'll take fifth derivative of the transfer matrix at 0.
Yeah.
So you get non-local Hamiltonian.
Yeah.
Yeah, it will be 5 sides interacting instead of just even. So with your procedure, you're getting something different or the same Hamiltonian as higher derivative?
So what we can get, so in that case, we can get a new description of the same model, what is already there. So we could start with that longer range charge and get something, but eventually it should be related to this one. I never worked with it on how to make the relation. But what is very important that in many models that we have, you can prove that there is no smaller charge. And this you can prove explicitly. So for example, in this Polderic 6A model, the smallest Hamiltonian has 3 or 4 side interaction range. And you can prove really directly that there is no Hamiltonian of two side lengths which would commute with it. So that's why we know that the models, at least the models, are definitely new, because there is no smaller charge which commutes with it. Whereas in your example, you start from this Q5 and you are happy that it's a new integrable model, but eventually you go back and you see that, oh, it commutes with X exact Hamiltonian, so there is nothing new. I hope it answers the question.
Yes.
Yes.
Any more questions?
So let's thank the speaker again.
Thank you very much. Thank you.